Hello everyone, I'm Professor Harrison, and welcome back to our module on matrix algebra for finance. Today we're going to be covering multivariable optimization. Specifically, we're going to look at how you find the optimum of a function that depends on more than one variable. We're following Ruth, a PhD student building out her matrix-based methodology for her dissertation. Today she's working on the optimization chapter of her framework, finding the optimal allocation across two assets in a portfolio. She sits down at her desk to get started. Back in calculus, we covered partial derivatives. The partial derivative of a function measures how the function changes when you wiggle one variable while holding the others fixed. So if you have a function of two variables, you end up with two partial derivatives, one for each variable. What we want to do now is use those partial derivatives to find the optimum of a multivariable function. In single variable calculus, the way you find a candidate for a max or a min is to set the derivative equal to 0. The intuition is that if you're at a minimum or maximum, the function has no slope. It cannot be going up or down at the optimum. Otherwise, you could move a tiny bit and improve. The same logic carries over directly to multiple variables, but there's one twist. At the optimum of a multivariable function, the function cannot be sloped in any of the directions. So not in the first variable or in the second variable. So every single partial derivative has to be set to 0 at that point all at once. This gives us a nice clean condition. We collect all the partial derivatives into a single vector which we'll call the gradient. It's written with the upside down triangle symbol, nabla f, or sometimes it's just written grad f. The gradient is the vector whose components are the partial derivatives of the function. And the first order condition for an interior optimum is that the gradient equals the 0 vector. Every partial derivative is 0 at the same point. So the first order condition is really one vector equation that stands in for a stack of scalar equations, one for each variable. Solving that system gives us the candidate points where the optimum could potentially live. So what does this look like when it's applied? Ruth's framework says that expected utility is from a two-asset portfolio with a function that looks like this. Expected utility as a function of the two weights, W1 and W2, is 5 times W1 plus 6 times W2 minus W1 squared minus 2 times W2 squared minus W1 times W2. The linear terms capture the contribution to utility from the expected return on each asset. The quadratic terms capture the penalty from taking on extra risk, which is how much utility goes down as the portfolio takes on more variance. The weights W1 and W2 are the dollar shares of wealth that go into the asset 1 and asset 2 positions. The goal is to find the weights that make her expected utility as large as possible. We start by computing the gradient. The partial derivative of utility with respect to W1 holding W2 fixed is 5 minus 2W1 minus W2. The partial with respect to W2 holding W1 fixed is 6 minus 4W2 minus W1. So the gradient is the vector with those two entries stacked. Now we apply the first order condition. Setting the gradient equal to 0 gives us two equations. 2W1 plus W2 equals 5, and W1 plus 4W2 equals 6. Now we have a system of linear equations with two unknowns. Specifically, it's exactly the kind of system that we learned to solve in the subunit on linear systems. So we know that we can solve for the answer using Gaussian elimination on the augmented matrix. We stack the coefficients next to the right-hand sides. The augmented matrix has 2, 1, 5 on the top row and 1, 4, 6 on the bottom. To set up a clean pivot in the top left, we swap the rows. The top row becomes 1, 4, 6, and the bottom row becomes 2, 1, 5. To eliminate the 2 in the bottom left, we replace the bottom row with the bottom row minus 2 times the top row. The bottom row then ends up at 0, -7, -7. We scale that bottom row by -1 over 7, leaving 0, 1, 1. The last step is to eliminate the 4 above the second pivot. Replace the top row with the top row minus 4 times the bottom row, and the top row ends up at 1, 0, 2. We end up at reduced row echelon form, with the identity on the left and the column 2, 1 on the right. So we know W1 equals 2 and W2 equals 1. The critical point is W1 equals 2 and W2 equals 1. So we have a candidate where we could potentially maximize our utility. We know the gradient is going to be 0 there in both directions, which means that we cannot improve utility by wiggling in either direction a tiny bit. But the first order condition alone does not tell us whether this is a maximum, a minimum, or potentially even a saddle point. We still have to classify it, and that classification will come in the video on second derivatives. We will build the machinery for it in the next video. Ruth gets up from her desk. She is the first half of the optimization chapter. It's the half of the argument every portfolio decision in her portfolio framework is going to rest on. So that is the setup for multivariable optimization. The driving idea is that at an interior optimum, the function cannot be sloped in any direction. So every partial derivative has to be 0 at the same point. We collect those partials into the gradient, set the gradient equal to 0, and solve the resulting system of equations. The solutions are the candidate optimum points. These end up being the foundation for every optimization argument that follows in this course.